and welcome back to the first day of the conference on predictability in general relativity in the memory of Professor Yvonne Choke-Bruha. And we have two talks planned during this session. A quick note to all the participants, please post any questions that you have during the talk on Zoom chat. There's one participant called questions on Zoom. You can post your questions directly to that participant. Or alternatively, at the end of the talk, you can just raise your hand and ask the questions yourself. And I wanted to point out that this talk is being recorded, so it will be uploaded to YouTube soon after the conference and will be available for everyone to see. So it's my pleasure to introduce Professor Elena Giorgi from Columbia University today, who works on the stability of black holes as solutions to Einstein's equations, especially with an emphasis on the interaction between gravitational and electromagnetic radiation. Elena did her PhD with Kleineman and Wong from Columbia in 2019 and was a postdoc fellow with Franz Pretorius's group at Princeton for a couple of years before joining Columbia as faculty. And today she's going to tell us all about the nonlinear stability of black holes. So Elena, please, the stage is yours.
Thank you. Thank you so much for the invitation. Introduction is a great pleasure and honor always to talk about, in a conference in honor of Professor Yvonne Choke-Bruha. So, of course, is an inspiration and whose work has been fundamental in pretty much, setting up the stage for anything that I'm going to say today. So thank you so much for organizing this. And so my talk is going to be very much an overview on a topic that is kind of active, and it has also a central stage in the subject of mathematical general relativity, which is the stability of black holes, and more precisely the nonlinear stability. So I'm gonna touch on some recent results that I have with Kleineman and Schefter on the nonlinear stability of curved black holes. But what I'm going to say is hopefully going to be much more general than that and try to give really the sense of how this kind of proofs are obtained. So, but let's start from the basics. I'm not going to assume anything pretty much. And I'm just going to remind things that we all probably know, but what we're talking about here is in the set of general relativity and the Einstein equation, according to which a space-time, so our object of interest, is a four-dimensional manifold equipped with a Lorentzian metric G. So Lorentzian really means that its signature is minus, plus, 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 satisfying the Einstein equations, which are written here. So it's this combination of curvatures. So this is the Ricci curvature, -1/2 Ricci scalar times the metric. So this is a two-tensor that is encodes really properties about the curvature of the metric, is equal to some t, where t now is the stress, is called the stress energy momentum tensor, and it contains, you should think of it as containing all the information about the universe, the space-time that you want to consider. So if it has matter, if it has electromagnetic waves, if it contains neutrinos, or anything you want to think of, should be contained on this right-hand side. So this very nice looking equation is actually a system of second-order partial differential equations in the metric, because the curvature is an object at the level of two derivatives of the metric. So this is actually a very complicated system to study. So what are some examples of solutions of this equation? Well, the easiest one we can think of is what is called the Minkowski spacetime. So that's the manifold is really just R4, and the metric is the constant metric, the simplest constant Lorentzian metric you can think of. So there is this signature -1 and then three pluses, and then the negative signature, the coordinate associated to it with the node as t, and that represents time. And while the remaining three-dimensional Euclidean metric is the usual metric on an Euclidean space in 3D. And this space-time describes the geometry of special relativity. So here, I already set up the speed of light to be equal to 1. Normally, you would have here a c square, where c is the speed of light. That kind of allows you to use this space, this metric, as describing a universe where that respects the laws of special relativity, in particular that nothing can travel faster than the speed of light, nothing massive, and the light itself travels along cones of slope c. And in fact, this allows to define for each vector on Minkowski spacetime, a classification of those according to their norm. So since now it's not a Riemannian norm, it's Lorentzian, we may very well have vectors that have norm less than 0, we call them time-like, equal to 0, we call them null or light-like, and greater than 0, we call them space-like. And so in particular, to each point in Minkowski spacetime, we can associate a light cone that precisely describes, makes the distinction between these types of vectors, in the sense that if you're a null vector, you're going to be tangent to the cone, or if you're a time-like vector, you're going to be pointing inside the cone. And for space-like, you're pointing outside the cone. And so according to special relativity, anything that is massive, like us, cannot travel faster than the speed of light, so they're going to in a space-time diagram where the time is a vertical, they're going to describe curves which lie entirely inside this light cone. So this is Minkowski space-time, but of course, any tangent space of a four-dimensional Lorentzian manifold can be locally be realized as a Minkowski space-time. So this classification is true for any tangent vectors on a Lorentzian matrix. So this classification is very important in relativity. Now, what about general relativity? So that's the theory that Einstein developed in 10 years after the one of special relativity. Well, that predicts the existence of black hole spacetime. So that it's kind of it's a theory that now allows for the presence of matter, and it allows for also the concentrations of gravity, and those black holes, which of course are going to be really the topic of my talk, are spacetime. Spacetime was metric, approaches Minkowski at infinity, so that's what we call asymptotically flat, and they contain but they contain also a black hole region, such that observers and signals originating there cannot reach infinity. So we should really think about this as being very different from Minkowski, where we have all these light cones that are kind of the same everywhere. Here, there is a region, here it's kind of depicted here in this. This is this image from the Nobel Prize Committee when Roger Penrose won the Nobel Prize. So here you see that some collapsing matter can create this region where now the light cones are tilted towards the region. They have become tangent to the boundary of this region, so that anything that travels as fast as the speed of light or slower than the speed of light cannot get out of it and get back out there, reach a place that it's infinitely far. So this is sort of the significance of a black hole region, and its boundary, it's called the event horizon. It's a null hypersurface. So this it's kind of a nice picture, but the way we normally represent this these black holes are through what are called Penrose diagrams. So those are 1+1 dimensional representation of spacetime. So you can think of suppressing two spatial dimensions. In particular, you can think of having this representation in spherical symmetry, so that each point of this diagram represents a sphere, same Minkowski. You only keep the t direction, the r direction, or radial direction. You see what the Penrose diagram do is to compactify what is called null infinity, what is called, you know, the infinity of that is reached by all curves that are null and don't fall in don't yeah, all curves that are null that are future directed. So that's this is the Penrose diagram of Minkowski. And if we are thinking about what would be then a Penrose diagram of a black hole, then we would actually have a region that is very close to Minkowski, very similar, I mean, very similar looking to Minkowski. That's the domain of outer communication, the exterior region outside the black hole. But then we will also have an event horizon, so this null hypersurface, with a region that now is actually is such that you can see if you have a curve that crosses the event horizon, then and this curve is time-like or null, then it will not be able to get out of it the moment it has crossed the event horizon. So that's and so that this represents a black hole region. What are some explicit solutions of black holes? So this is, you know, apart from the picture, you know, the Penrose diagram. So that was the Penrose diagram of Schwarzschild. So that's the first explicit solution that was found, and that it's, you know, it's also pretty nice looking and easy to write. And so it's this one here. So it was found in 1916, and right after Einstein wrote his equations. And you can see this is very interesting, looking, because if this parameter, so it depends on a parameter m, if this parameter m is equal to 0, this reduces to Minkowski space written in spherical coordinates. But if m is there, this is not flat. It still has Ricci curvature equal to 0, so that the solution of the Einstein equation in vacuum, when there is no matter, there is no stress energy momentum tensor, but somehow this represents the space-time really associated to an isolated body of mass m. So you can think of it as a star. And that's very interesting, very useful, of course. But there is something, you know, funny about this metric, that, you know, you see at r equal to m, these coefficients seem to vanish and they seem to blow up. And of course, r equal to m is actually the location of the event horizon. So there is no really any singularity that it's happening there. It's only this geometrical fact that the light cones become tangent to it, and then there is a region when r is less equal than to m where all the light cones are tilted towards and light cannot get out of it. So that's the first solution that was found. Right after, it was found like something that is very much related to it. It's called Rice and Nordstrom, now has two parameters, m and q. It's actually a solution to the Einstein-Maxwell equation. So Ricci is not equal to 0, but it's given in terms of a quadratic expression into the electromagnetic tensor that satisfies the Maxwell equations. And it's really very similar. It's still spherically symmetric, so it has this piece, but now in this coefficient, it has an extra plus q squared over r squared. More interesting, something that the solution is much more interesting than in the sense that it has lots of additional features with respect to Schwarzschild, is the Kerr spacetime that was found much later, only in the 1963. And here I'm not writing it down, but it's an explicit solution. It's not that bad. It's okay. It's not as simple as Schwarzschild, but it's also not that bad. It has a few more sine and cosine. But it also involves two parameters now. So it's m and a. And now the a represents the broken spherical symmetry. So if a is equal to 0, you just recover the Schwarzschild, so the spherically symmetric solution. But for a different from 0, you don't have anymore this piece, the spherically symmetric piece, but you have something, a metric that describes something that is only axially symmetric, so it rotates around an axis of symmetry with some angular momentum that is parameterized by a. So that's also a solution to the Einstein vacuum equation, and it was very important because, of course, if we think about parameterizing objects, you can think of stars or whatever, black holes that are kind of more physical, then you expect that something that is axially symmetric is much more reasonable, is much more similar to the reality than something that is spherically symmetric, that is just doesn't rotate at all. So the cache solution has, of course, played an important role, and that's kind of the main protagonist of these solutions. There is also a natural extension of care, just like Rice and Nordstrom is an extension of Schwarzschild. There is something that's called Kerr-Newman that now puts together all these solutions by having three parameters, M, A, and Q, which are now the mass, the rotation, and the charge of the black hole, which is a rotating solution to the Einstein-Maxwell equation. So these are the solutions, and I can point out here there are some ranges of these parameters, and those are requested so that there is a black hole, in fact. So technically speaking, if you're not in those ranges, this event horizon, so this coefficient, let's say, does not have a root, so you don't have an event horizon, you don't have a black hole, but you have something you can interpret this as some naked singularity. So that's the range, that's the full range that is allowed to have a black hole. And of course, that kind of, for example, in the case of Kerr, it relates the spinning, like the velocity of the black hole to its mass. So if something is very slowly rotating, it's much similar to Schwarzschild. If it's very fastly rotating, it's gonna be more and more more and more we'll have more and more like Kerr-like features. And so these are the black hole explicit solutions, and they all have, as I mentioned, symmetry is like spherical symmetry, axial symmetry, but the most important symmetry that they have actually is what is called stationarity. So the fact that all of these do not depend on time, they're not dynamical. And this is why they were found. I mean, it's easier to find something that it's stationary, it's an equilibrium point, as opposed to something that is dynamical. So that was crucial. But of course, it means that there's also like a limitation in the description of this, that these explicit solutions can give us a description of, let's say, real black holes, which of course are dynamical. So one should somehow would have to understand how the dynamics, how the Einstein equation realizes itself as a dynamical theory in these black holes. And that's where we get precisely to Choquet-Blois contribution to the fact that the Einstein equation can be formulated as a quasi-linear hyperbolic system of PDE, which in wave coordinates can be written as a box of D'Alembert associated to the D'Alembert G, given in terms of non-linearities of the metric in its first derivatives. And it's this expression, this formulation, that allowed Yvon Choquet-Blois to prove a fundamental theorem that says any initial data for the Einstein equation. So those are data given on a three-dimensional hypersurface that satisfy the constraint equations. They give rise to a solution that is smooth, it's local in time, and this solution is geometrically unique. That's our work with Guéroche. So that's a fundamental theorem that, in a certain sense, really we can think of it as being the beginning of the subject of mathematical general relativity, meaning that now we can solve, apart from finding explicit solutions a little bit by using the symmetries and or by accident or somehow, we can systematically think of solutions to the Einstein equation as being born out of initial data. So there is an initial value formulation in terms of PDE. So it has become, with this theorem, general relativity has become a branch of PDE in the mathematical community. And this theorem fundamentally tells us that there is a local in time solution. Now, the question of stability, which is in the title of my talk, starts with this local well-posedness results, and then asks and is interested in what is the long time behavior of solutions to the Einstein equation. So beyond what Schoenberg's theorem tells us that there exists this solution that is local in time, so for some short time. We want to ask what happens for a long time to this solution. And now why do we care about stability? Just let me spend a second try to motivate why we would be interested in this in this concept, right? So stability, of course, is a very general concept in science. You can say it's the ability of an object to change in a controlled manner under small perturbations. We should have well in mind, this kind of two cases where you have a ball in the bottom of a hill, or a ball placed on the top of a hill, and where if you move the ball in the bottom of a hill a little bit, it will oscillate around its position, then eventually go back to it. Well, if you move a little bit the ball and the top of a hill, it will just fall down and will never go back to its original position unless you're spending energy to do it. So and these two configurations are clearly very different physically, because one is a stable and one is unstable configuration. So if there is a small perturbation, one changes in a controlled manner, it doesn't change very much, and the other one changes radically, even though they, if you analyze them from a point of view of some equilibrium point for this for gravitational system in this case, they both represent legitimate mathematical solution, a legitimate equilibrium point for this problem. Just like the pendulum that oscillates downward or upward, the position of being exactly upward or downward is an equilibrium point, but one being stable, one being unstable, you actually don't see the pendulum upward ever. And so the question of stability relates to the fact that it is an empirical observation, especially now that we have gathered so many evidence of the existence of black holes, detection of gravitational waves, the realization of pictures like this one, images of black holes that were obtained by the Event Horizon Telescope. So we have so many empirical observations that there are black holes, and those black holes are stable, in the sense that there are so many perturbations that come to them, and they still remain they still maintain the same properties, the same main adjectives. But in all these computations and analysis that the physicists do to get this empirical observation, they really sort of assume, they use the assumption that what they're observing is a Kerr solution. And so in order to justify the fact that this Kerr family, which is a mathematical solution, so again, it's just a mathematical solution, just like the position of this ball upward, or there's the position of this ball downward. In order for it to be to make sense of it as representing something that is in the real world, some astrophysical black holes, it should at least be stable as solutions for the Einstein equation. Otherwise, we may be looking at something that is a legitimate mathematical solution like this position, but doesn't really take place in reality because it's unstable. So this is kind of one of the motivation why we want to understand the stability of this of these families. And so technically, now we're more on the technical side, what does stability really mean? There are different kinds of stabilities that you can think of in an increasing level of difficulty. So you can think of having, since the Einstein equation can be realized as a wave equation, you can think of taking the simplest possible case is taking just scalar wave equations on black holes and showing that this solution, these PDs are stable, and it's something that has been done in the early 2000s in Schwarzschild, as a Northman, and in Kerr and Kerr-Newman arriving to the the final sort of the final statement by the Fermat-Solnjansky-Shlomentov-Rothman saying that all these solutions are stable in the full range of the Kerr family, where A is really less equal than M. Or you can look at the Einstein equation, so taking really the Einstein equation and linearizing it. So instead of having a non-linear system of PD, now you have a linear system, linearizing around a linear solution and study this linear operator. So this has many recent works that started with the one by the Fermat-Solnjansky in 2016 in Schwarzschild, and something I've been working on it was in my thesis, that the linear stability of the Rice and Nordstrom, and then there also been works for so the proof of the linear stability of Kerr in 2019, and also very recently of Kerr-Newman. So this is a very active area of research where many people have contributed. So this is and it is of course like a huge step from scalar wave, because it's the full Einstein equation, even though it's linearized around a solution. So some of the difficulties are the nonlinear part in particular don't appear, but this is the full system of linearized gravity. So it is a huge improvement from the scalar waves. And then what about the nonlinear stability? So actually studying the stability of the full Einstein equation, so without linearization. Now let me put back in the picture then what is the case of Minkowski. So even for Minkowski, this is highly non-trivial. I'm gonna come back to this in a second. This was proved by Christopher Kleineman in the 90s, and now just very recently there been work for the nonlinear stability of Schwarzschild. So by Kleineman-Sheftel in polarized in the polarized axisymmetric case, and by the Fermat-Solnjansky-Taylor for initial data they belong to a dimension 3 moduli space. And these restrictions are somewhat necessary in Schwarzschild to get a statement for nonlinear stability of Schwarzschild, because Schwarzschild is naturally embedded in the Kerr family. So in the nonlinear stability, you would have in general you would expect to converge to a Kerr family. So these restrictions are somewhat needed to avoid that. And what I'm going to say a little bit more about is our proof that is combined, that it's a proof that comes out of 5 works, 3 by Kleineman-Sheftel, 1 by Shen, and 1 by me, Kleineman-Sheftel, to obtain the nonlinear stability of the very slowly rotating Kerr family. So let me just spend a few words saying why did I put back Minkowski in the picture? Why did I write Minkowski here and not in the, let's say, the scalar wave of the linear stability? Well, the scalar wave, let's say, case of Minkowski, it's something that is now considered classical, because it's something that, for example, is taught in a PDE class, right? So what happens to the wave equation in Minkowski space? The kind of you have this D'Alembert formula, you have this many things you can do the Fourier transform. There's many ways you can deduce, let's say, decay for solutions to the wave equation in Minkowski space. Why is the nonlinear stability not a classical thing, or something that is that somehow it's difficult? Well, the reason why it's difficult is because nonlinear wave equations in Minkowski are difficult. So in fact, for example, if you consider like some wave equation, instead of being box equals 0, brings to some nonlinearities, such as the tip equals 0, and takes some initial data equal to epsilon. Now, if epsilon is equal to 0, by uniqueness, so if you have 0 initial data, by uniqueness, the solution will be also 0. And so you have a global in time, so solution is identically 0. But if epsilon is greater than 0, the solution will actually blow up in finite time. So this shows that the trivial solution of this, the trivial solution, sorry, the 0 solution of this equation is not stable for this nonlinear equation. So that's somewhat problematic if you think that this can represent the structure of your Einstein equation. But So in particular, something similar could hold for the Einstein equation. So that you have perturbations of the trivial solution, which is Minkowski, could blow up maybe infinite time. But well, they don't. And that's a theorem by Christodoulou-Kleinerman that, again, it's a fundamental theorem of, very complicated, very long. It's like a 500-page book that shows that Minkowski spacetime is nonlinear stable as solution to the Einstein vacuum equation. And there are many aspects to this proof. Let me just remind some of them. So the first is the geometrical construction of the space-time. So instead of using the wave coordinates that were used by Choquet-Brouat in our proof, they use vector fields that are geometrically defined along the manifold. So these are like this, and they these two null directions, the two preferred null directions of any of perturbations of Minkowski. So those are used to construct the space-time geometrically. Then they use the vector field method. This was developed by Kleinerman, precisely in the study of these nonlinear wave equations in the 80s. And the crucial way to deal with those is to treat the Einstein equation which equals 0, to actually study this through the projection of the Bianchi identities. And they become now a hyperbolic system of PDEs for systems, for tensors on this surface foliation as generated by these two null directions. And then finally, the crucial aspect is that there is something that, again, this was something that was introduced by Kleinerman for nonlinear wave equation. It's called the null condition, in the sense that that says that the nonlinear terms that are bad, the ones that drive the blow up, such as the d tip psi square in that example, are not present in the Einstein equation. So that's these three aspects kind of give the like the fundamental reason why this theorem is true when Minkowski spacetime is stable. Now, what would instead a theorem on nonlinear stability of black hole family look like? So you can think of this as being a very general statement that you can apply to those cases that I mentioned. So here I'm mostly concentrating on the asymptotically flat cases. So I didn't mention that there's also nonlinear stability results for black holes with positive cosmological constants. Here I'm really talking about having a Fisher null infinity. So these are in the asymptotically flat case. So a general theorem will look like this. We'll say that general initial data that are close to a member of a black hole family. So think about your favorite black hole family. If you start initial data that are sufficiently close to a member of that, well, those initial data will evolve according to the Einstein equation to a space-time which still has a complete future null infinity and a complete event horizon, and it asymptotes back to a member of the same black hole family as time goes to infinity. So if you wait long enough, this initial data will asymptote another member of the black hole family. So it will not asymptote necessarily to the same member, because you may have a change in the parameter. You may have a change in mass and rotation and charge. So the picture you should have in mind that you have your black hole. So we're talking about the exterior of the black hole. You have an horizon, you have an null infinity, and you have some initial data. Now the nonlinear stability, you forget. So after you have this set up, you forget where you are, and you don't know where you are anymore. You only know what is your initial data. So you don't have the background that helps you. So that's really the difference with the linear theory. You just have the initial data, and what you want to construct the evolution to this initial data, and to prove that at the end of the day, this will also have a future null infinity and a future event horizon. Okay, so this is kind of the statement. So what is the setup of the proof? Well, the setup of the proof relies on a continuity argument. So it's something that it's very, very, very basic. I'll try to just give the very basics of how the proof is set up. And continuity argument, it kind of develops in the following way. You want to show that the the development, so the evolution of your perturbed data is constructing as a limiting sequence of finite spacetimes. And now each step of this finite spacetime is governed by final time that defines a subregion of spacetime that has some set of bootstrap assumptions. We're going to get back to this in a second. But let's have a picture in mind. So we have our initial data. So remember, we don't know anymore where it lives or where it comes from. We only know that we have some initial data. Now, what we're going to set up is a finite region. It's this region that is bounded by this blue line. It's a finite region on which we have some assumptions. So now, first of all, you may ask why is this region bounded by this two null hypersurface as opposed to sigma 0? So that's not that important. In fact, you can very well use a space-like hypersurface. This was as well, it was done in Minkowski space. In this most recent proofs, the initial data is always set up on two null hypersurfaces. It's just more convenient. You can think of it you can think as passing from a space-like hypersurface to these two null hypersurfaces is not. So basically, the treatment of passing the information from this space-like to this null, it's somewhat related to the bit of Minkowski space because this is still like a global, semi-global region, but somehow this can be treated as in Minkowski space, or even more precisely in exterior of Minkowski space, as Zarbeklan and Van Niccolo, for example. So you can think of having some initial data on these two null hypersurfaces 0 and C bar 0, and you have some final time that describes, like, the end, really the boundary of your finite region. And so this could be, so this is drawn in this way because it could, for example, be made also of pieces of null, like null pieces, but it's not that important. What you should have in mind is just it's a finite region of space-time. And now the continuity argument relies on the following obvious fact that if you have a subset of an interval, which is the interval 0 infinity, which is non-empty, open and closed, then that's the entire interval. That's the definition of being connected. And so what we're going to consider as B, what we're going to apply the continuity argument to, is the following: are all this time t final, such that two things, bootstrap and gauge assumptions, hold in this region M final. Okay, so let's call this blue region M final. Now, why is this what we want? Well, because if this subset is not empty, open, and closed, then it's the whole interval. So then it's 0 infinity. So then it means that these assumptions can actually hold. They hold for that time that goes to infinity. So we have a global solution that in particular will asymptote, and these assumptions are going to tell us how they asymptote to our member of the family. So this is gonna give precisely what we want, the global solution that asymptote back to a member of the family. So this is really what all we need. We need to show that this thing is non-empty, open, and closed. But what is this thing? So what are bootstrap and gauge assumptions? So let me try to give a sense of these two magic words, right? So yeah, I don't know about you, but I never heard the word bootstrap used by anyone who's not a mathematician, or even more than that, who's not like an analyst. And in fact, but it is a word in English, and it means to make use of existing resources to raise oneself to a new situation, to rely entirely on one's effort, to be self-generating, self-sustaining. Okay, so the idea is that being like a bootstrap is something that bootstrap assumptions will be assumptions that are assumptions, but they're not really assumptions coming out of nowhere. They're assumptions that will allow to precisely prove that set is non-empty, open, and closed. So they are self-generating, self-sustaining, and we're gonna see in a second how precisely this is done. And now the word gauge assumption. Now gauge is a bit of it's more of a kind of charged word, in a sense that like everyone, every mathematician, in every field is used, it is used differently. And many people may mean different things. What I mean by gauge assumption, or here in the context of general relativity, is the fact that the Einstein equation is a tensorial equation, it's an equation of a tensor. And so if I have a solution for it, then any pullback to any diffeomorphism of that solution is also an equivalent solution. That's because it's a tensorial equation. So that's why we define tensors. We define tensors so that those are objects that do not depend on the choice of coordinates. So somehow, what a gauge assumption is something. It's a condition on coordinates, or on this diffeomorphism through which you're looking at your solution, and you need to have those assumptions, because otherwise you won't be able to prove any decay, since you have a tensorial equation. There is too much freedom otherwise. So these are the two things that have to be that we have to look at in our set. We want to prove that it's non-empty, open and closed. Okay, so bootstrap assumptions, they measure in a quantitative way how the bootstrap region is close to the perturbed family of black holes. So schematically, they're given by something like this. So there's a difference, the difference between the metric and the one I want to show them converging to, and also for the Christoffel symbols and the curvature. So the sup of this should be less equal than epsilon, so should be somewhat small, for some epsilon, some parameter, or some smallness parameter. Now this is very schematic. What in reality what you have is a very specific set of bootstrap assumptions for each component of the metric, of the curvature, and so on. You have a very specific, decay. I mean, a very, very specific norm that is less equal than epsilon. But let's say schematically, that's what you have. Well, gauge assumptions in all these works that I mentioned are normalized towards the future, even though sometimes more than one normalization is necessary. So what you should have in mind is really that, again, going back to our picture, we have our finite region where some bootstrap assumptions of size epsilon hold, and then you have a choice of gauge that most of the times that takes place on the final time, but you also have some gauge assumptions on the full finite region. And now just the initial data instead will be of size epsilon 0, some different epsilon 0 that in general will be much smaller than the size of the bootstrap assumptions. Okay, so then let's see, how do we prove that this set is non-empty, open and closed? Well, the fact that it's non-empty relies on the fact that you have some initial data, so you can relate these things. You can use the fact that initial data, you have a small perturbation to show that at time 0, you can get this assumption satisfied. Now, open, what does it mean for this set to be open? It means if you have a time in this B, so if you have this finite region that satisfies bootstrap and gauge assumptions, then for a small delta, you can extend this region a little bit and still have the bootstrap and gauge assumptions satisfied. Now, to have the bootstrap assumptions to be still satisfied, the crucial point is to have them improved. So what that means is that you use the smallness of the initial data and the gauge assumption to show that actually all your bootstraps that you thought were just less equal than epsilon, well, they're actually less equal than something that is proportional to epsilon 0, which, since epsilon 0 is much smaller than epsilon, is actually strictly less than epsilon. So then by continuity, you can extend the space-time a little bit and still being less equal than epsilon. So this, so if you can prove that, if you can prove that your bootstrap assumptions, again, since they have this self-relying system that they actually improve themselves, then you show that for this T plus delta, bootstrap assumptions are also satisfied. And then you also need to construct the gauge assumptions for this T plus delta. This means constructing the gauge, the choice of gauge for the extended space-time. And now the closeness, so the fact that, let's say, if you have a sequence of these times in this set, then the endpoint is also in the set. It kind of relies on higher order CK estimates that you obtain in the process of showing that it's open, and some Arzelà-Ascoli theorem to show convergence. So really, the heart of the matter. So if you prove they are non-empty, open and closed, then you have the B is the whole interval, and therefore the solution is global. You prove what you want. So the heart of the matter here is to improve these bootstrap assumptions. How do we improve the bootstrap assumption? Well, we need to use the hyperbolic nature of the Einstein equation. So those Bianchi identities that represent the Einstein equation are involved in tangled system for the metric curvature and Christoffel symbols. But there are some components of the curvature. So those are, if you take the Riemann curvature and you evaluate it with two of the null directions, so this E3 and E4, they are these quantities vanish in Kerr. They satisfy wave equations decoupled by all other quantities in linear theory, so this is called the Tukowski equation, and are almost gauge invariant. So if you change of a size epsilon your gauge, they always change, they only change up to epsilon squared terms. So the strategy really to improve the bootstrap assumptions is to first improve the bootstrap assumptions for these quantities, the ones that are these almost gauge invariant quantities, and then improve them, and then use them, use those to improve the bootstrap assumptions for the remaining quantities. So this is the strategy. Now, how do we use these Tukowski equations? Well, so if I call this T alpha, so it's this kind of, you see, this is a kind of a wave equation with some first order terms of potential. In nonlinear theory, we will have a right-hand side. We will not have equal to 0. But this right-hand side is given in terms of objects which satisfy the bootstrap assumption. So somehow you hope to control them using the bootstrap assumptions. But it turns out that even the linear Tukowski equation is very difficult to analyze because of its first order term. So here there is like a sub-strategy in studying those that was introduced by the Fermos-Olsky-Roniaski for Schwarzschild and then extended by Ma and Fermos-Olsky-Roniaski in Kerr, that the idea is to consider higher order quantities that satisfy more treatable equations. In fact, equations that I'm going to read in a second are called generalized Regge-Wheeler equation that can pretty much be analyzed as the scalar wave equation. Okay, how do we analyze the scalar wave equation? Let me say as an aside, there are a few issues. One of the most basic issues in analyzing wave equation of black holes, which, as I said, it's something that it's somewhat understood now, as developed in the early 2000s, is to deal with the existence of trapped null geodesics that remarkably those are unstable, and those are the ones that tend to sort of live at the photon sphere. So then we have that some of these estimates have to degenerate there, but that's they can still hold these estimates. And in the case of Kerr, we have also super radiance, that the stationary Hilling vector field is time-like on the outside of the ergo region. So the associated conserved energy fails to be positive definite. And if A is much smaller than M, these two problems kind of get simplified and can be understood in physical space. So for example, by using the method by Anderson-Blue, which is the method that we use in our proof of nonlinear stability of Kerr, precisely because of this of its power of being can be used in physical spaces, so can be easily generalized to the nonlinear picture. But in the full sub-extremal range, the interaction between these two things for now can only be understood in frequency spaces, as in the work of the Fermos-Roniaski, Schlaven, and Rockman. Okay, so but somehow let's think that we know how to deal with the wave equation. So what do we do from the Tukowski equation? Well, we define the higher order, like some higher order quantity that is at the level of two extra derivatives of the metric, of the curvature. So the curvature is already two derivatives of the matrix. We go at something that is at the level of two derivatives of the curvature. And it's a very specific expression that has lots of good properties. In particular, it satisfies a nonlinear wave equation that is, if A is equal to 0, so in Schwarzschild, it will simply reduce to the Lambertian minus a potential equal to nonlinearities. Now, in the case of Kerr, we still have a first order term, and we have a coupling with the curvature terms. But this first of all, the first order term is still fine because it has a very special expression, so still satisfies good divergence properties. And because of this right-hand side, so because of this coupling, one has to view this wave equation as coupled with the defining definition for psi. And the error terms, crucially, according to bootstrap assumption, they decay, fast enough to close the argument. So that's kind of the strategy of improving the bootstrap assumption for this alpha and alpha bar. So we want to improve bootstrap assumptions for alpha and alpha bar. We go to this higher order quantities that satisfies this generalized Reggie-Wheeler equation that we can analyze directly. Since it's a wave equation, its estimates are going to be based in terms of the initial data, because it's a wave equation, has initial value formulation. In terms of initial data, so we're going to have all the estimates are improved by, they're going to be now bounded by some, let's equal a constant times epsilon 0, which can be taken to be much smaller, which can be taken to be less than epsilon. So we have improved the bootstrap assumptions for this alpha and alpha bar. So at this stage, we still have our finite region, and we have improved at least, some of those. We improved assumptions for alpha, this alpha and alpha bar. And now the remaining strategy would be to use those to improve everything else. Now, here, alpha and alpha bar are gauge invariant. So whatever we did till now did not depend very much on the gauge. I mean, there are some subtleties, but it didn't depend very much on the gauge. What we're going to do from now on is going to depend very, very much on the gauge. So we will now have to set up a gauge. Now, as a preamble to talking about gauge, let me mention that, in care, there is a difficulty, in addition to Schwarzschild, for example, or of course Minkowski, is the fact that the frames that are used to study the Minkowski equation are non-integrable. So what does it mean? Well, as it was already done in the case of Minkowski space, to which point of your finite space time you can associate an null frame, in this E3, E4, and this orthogonal E1 and E2. But now, for the Minkowski equation in care, to use the Minkowski equation in care, it satisfies by those alpha and alpha bar that I said are defined in terms of sum E3 and E4. And those, in order for those to vanish and satisfy the Minkowski equation, the C3 and E4 need to be a principal null frame, which diagonalizes the curvature. That turns out that is not integrable in Frobenius sense. So what does that mean? It means if you take this E3 and E4, you take the tangent space. So you take the orthogonal space to the C3, 4 in the tangent space. Well, this vector space is not tangent to a surface even locally. So in fact, there is no sphere here. It's actually a two-plane distribution, and that's because these two vectors in the orthogonal are not. If two vectors are in the orthogonal, their commutator is not necessarily in the orthogonal. So you have the Frobenius theorem. This is equivalent of not being realized as a tangent as a tangent space of a surface. So that creates it's a difficulty, but we can nevertheless overcome it by considering transformation into integrable frames. I constantly have to change. If you want to use, for example, elliptic estimates on spheres, you have to constantly change these frames into frames which are integrable. So this is a difficulty. What are the gauge? So let me just say a few words about the gauge assumptions. In particular, I want to mention how they are set up. So this is the picture from the actual paper. This is the setup of the proof in Kahneman-Schefter. So you see, this is the finite region I was talking about. And as I mentioned, the gauge assumptions are given in the final time. In particular, in this work, that imposes the final sphere S star and the hypersurface sigma star. So this piece here, and now this sphere S star is a codimension 2 compact surface in the space that is unrelated to the initial condition, on which you have you impose your gauge assumptions are some conditions are the same as in Schwarzschild, and that's something that you can do it because this region is far away. This region will go into being something that is far away in the limiting process. Where R is very large, so the contribution from care with respect to Schwarzschild will be very small. And so these are gauge conditions are set up here, and of course there are also gauge conditions that are set up in the remaining part that allow to cook up a very specific hierarchy to deduce from this alpha and alpha bar that we control from the wave equation to deduce all the other quantities through basically transport estimates from this S star sigma star, where you have a gauge assumptions towards the rest of the space time. So this is like an important part, but there are some very technical definitions that I'm not gonna go into. Let me just mention how, as a final thing, how then you compute the mass and the angular momentum, of this space. Well, the final sphere S star is also important to do that. So it's under that final sphere that you should think that, again, in the limiting process, this final sphere would sort of will be sent to infinity, and so in the limiting process it will capture really the full change of mass and angular momentum. But at each stage you actually have to define what is now the new the new mass and the new angular momentum to which you're comparing everything in your bootstrap assumptions. And this is done through a definition to a quasi-local mass. This is the Hawking mass of the sphere S star. And the angular momentum, so I'm not gonna define everything here, but this beta is a curvature component of your space time, and this is somewhat like an associated projection on the spherical harmonics on this curvature, and it's this combination that is used as a definition of angular momentum. So these two are constants that are defined on the spheres and then transported as constants again along the sigma star and everywhere else, and they identify the final mass and angular momentum. There is also something else that it's a center of mass frame. But since this approach is somewhat one can think of it a bit unusual, I mean, this setting up of the gauge assumptions on a faraway sphere. Well, since these do not make direct reference to initial condition, when they are transported along sigma star, there is they induce a new foliation initial data, and this sort of causes a shift to the center of mass. This is something that in physics is called gravitational wave recoil, and it's something that you just have to take into account in the process of the final, like in the final asymptotics. And so, but in this way, this is how you identify the parameters that allow you to define the bootstrap assumptions, which are improved through this gauge invariant and then gauge dependent quantities, and that's the crucial part of showing that set is open, and eventually the set is shown to be non-empty, open and closed, and so the proof is complete. So that's kind of an overview of this proof, and of course unfortunately it's a very long proof, but really the main parts are really this improvement of bootstrap assumptions, and hopefully this gives a kind of a sense of how this proof goes. And with this I want to thank you for your attention.
Thank you very much, Elena. That was a very eloquent and clear talk. So let's move on to questions. Just a reminder, people can just raise their hand right now and ask questions.
Yeah, we have one question which was sent to questions by Virinchi Ralabandi. Virinchi, would you like to ask the question directly, or shall I read it out? You can raise your hand if you want to ask the question directly, or I can just read it out.
Okay.
Sorry,
maybe
can
I
you hear
can
me?
read out the question. Yeah, Sumati, we can
Yeah,
hear
can
you.
you hear me? Yeah. So yeah, so okay, so it's he's saying the person saying that they're in a crowded room, so it's better if I read it out. So but first I think we should just thank the speaker. I'm not sure I want to do my clapping. But okay, so let me read out the question. It's How much is known about this topic in higher dimensions? For example, is Schwarzschild nonlinearly stable in higher dimensions? Alternatively, if rotation is allowed, is it possible, for example, that a Myers-Berry solution could evolve to a black ring upon perturbation?
Yeah, these are very, very good questions. So for the higher dimensional Schwarzschild, I think that there is no proof of nonlinear stability of higher dimensional Schwarzschild, but there are proofs of, there's a proof by Wong, Keller, and Hong of the linear stability of Schwarzschild in higher dimensions. So I think it's up to dimension 6, if I remember correctly. So there is, but then there is, yeah, for higher dimensions somehow there was there's a difficulty in the proof. And that's for the linear stability. So I think it's otherwise it's open. I mean, for the nonlinear stability, it's somewhat open. Yeah, I'm not even sure I can give a good sense of the the difficulties in the higher dimension. I mean, for the higher dimensional Schwarzschild, it's just some technical aspects of it become difficult if you have a too high of a dimension. I mean, it's precisely in that analyzing that equation, the Reggie-Wheeler equation, that what you do in the analysis somehow gets influenced by the dimensions. And about the Myers-Berry, so I think that's an even more delicate kind of setting, because you can have you can have different rotations there, and in a higher dimension, there are also this black string or black ring, as that you said, they can pop up, so you don't necessarily have your care. You can even think of you can have convergence into different space-time. So yeah, that's it's very much uncharted territory. I mean, there have been works for the scalar wave equation in black rings and black strings, and in I'm not sure about Myers-Berry, but so it's very far from something like nonlinear stability. But yeah, I don't know. I can't say like all the updated references about that, but it's definitely very, very interesting direction. It's not very much explored for now.
Karthik, Prabhu, do you want to maybe just say your question?
Yeah. So in all these stability proofs, there's also always a question of whether the decay you get in the future is optimal or not. And I wanted to ask, what really is the obstruction to getting optimal decay? Is it, the bootstrap? Is it gauge? Or is it really the nonlinearity of the equation?
So it depends also what you mean by optimal. For example, if you think in terms of optimize as in terms of like price law, then it's a bit those things are a bit unrelated, because are unrelated to the bootstrap assumptions, in the sense that I mean the assumptions that you give in the bootstrap assumptions are somehow in a certain sense optimal, in the sense that they're what you need for it to work. Right, they're what you need for it to be bootstrap, so to be self-relying, right? So if you give too little, then you won't be able to close them. So you won't be able to use the bootstrap assumptions to improve themselves. If you give too much, it's just not gonna be true. Right? If you, for example, if you give something that is not, you just won't be able. You're just too restrictive on your bootstrap assumption. So what you can have, so the bootstrap assumptions can be dependent on the decay that you have on your initial data. So that's like a little bit of a different story. So if you can have stronger or faster, in fact, there are different proofs. For example, it's a bit of Minkowski space, or depending on the the decays that you have on your initial data, you may have different outcome in the decay from the bootstrap assumptions and therefore from your solution. So that's it really depends on what you mean by optimal. If you care about the optimal decay in T, optimal decay in R, in which region, and so, and in let's say the bootstrap assumptions normally try to sort of summarize the like all of this optimal, all of the assumptions that you really need. Even though you may, if you do some refinements, you may get something more, but maybe are not needed to close the argument. And so, for example, we don't do that, and we don't get like the optimal decay, let's say in R for the maximal curvature for the maximal curvature component. But it's something that it's so similar to the optimal that it's enough to use it. So yeah, it depends. You can always refine. There are some things that can be refined, some things that are necessary and optimal as they are. But it really depends on your interest in and what you mean by optimal, really.
Okay, great. Thanks.
Okay, so as questions, I'm going to ask a question because I'm not sure if there's anyone else who's got a raised hand. I want to ask a very general question about the nature of these stability arguments, and I mean also the nature of the definitions of stability. I understand the one is looking at growth and decay of modes and so on, growth versus decay of modes, and this is related to what Karthik was asking. But at the end of the day, because we are growing Lorentzian spacetime, you really want to ask a question, that Lorentzian spacetime that has been grown through a perturbation, how far it is from the initial, from the one that would have happened without the perturbation. And this distance between, the sort of distance between Lorentzian spacetimes, how do we quantify it in a meaningful way? It's a big open question in the field, and I'm just wondering whether these kinds of questions at all pop up when one is looking at nonlinear. I mean, whether these are techniques that can be used which are different from the sort of mode decay techniques to sort of put a metric on, or a distance function on closeness. So
right, yeah. So it is very different from this mode decay, because here, as you've seen, I've never mentioned modes because in fact we don't need any mode decomposition. And in fact so the distance you're talking about, so it's in here it's somewhat very like I don't know, somewhat rudimental way of computing the distances. So in the bootstrap assumptions are the way of measuring those distances, and there are, so again, bootstrap assumptions are there are many of them, and it's pages and pages, but most of them you can think of them as being really pointwise estimates, so pointwise norms. And so really the distance is measured explicitly in those in some coordinates that are constructed in a space-time, and this is a way of you measure the distance from your original, so your initial data, so the original, the curve that you would have evolved if you didn't perturb the initial data, and the ones you would have it does asymptote to after you perturb. So it is those norms don't really, they're somewhat very specific for each component, so they're given by bootstrap assumptions. I'm not sure how one would use them to give like an abstract definition of the distances. It's a very much it's something that's very much tailored to the problem and tailored to the decay that comes out of the wave equation that you get, and so it's yeah, it's hard to think of generalizing it. But I don't know. Yeah,
Yeah, I guess, I mean, in the case of having data, you already, I mean, you can use the Riemannian structures that are there. In terms of initial data, I guess my question is that, I mean, an example of something that the dynamics takes you away, quantifying it at a moment of time, I can see that. But then if you wanted to do it in a, from the full space-time perspective, that's a sort of, but yeah, thank you. Thanks.
yeah, I see what you mean.
Okay. If there are no more questions, I would wholeheartedly thank Elena once again for accepting the invitation to speak here and taking out the time and to prepare and deliver this talk. Thank you so much, Elena.
Thank you for having me. Thank you.
Thank you so much.
So our next speaker this evening is Thomas Baumgart. Okay, I see Thomas is here. Excellent. So hi, Thomas. Hopefully you can hear us.
Hello.
Yes. Hi.
So, okay, now should I share my screen or how do we do this?
So let me just say a quick word. So it is my pleasure to introduce Professor Thomas Baumgart from Bowdoin College. Thomas completed his PhD from the Ludwig Maximilian University in Munich, after which he did a couple of postdoctoral terms at Cornell and University of Illinois at Urbana-Champaign before joining Bowdoin's faculty in physics. Thomas is very well known for his work in numerical relativity, and it ranges from fundamental questions in 3+1 formulation to neutron star binary simulations. But perhaps he's even better known for his book on numerical relativity that he has co-authored with Stu Shapiro, and it's fairly standard reading around the world on the subject. And on a more personal note, Thomas has been closely associated with ICTS over the past several years, and we are very happy to have him speak here. So with that, I request Thomas to maybe share your screen and take it away.
Yeah, so thank you very much for the kind introduction. It's been a pleasure actually to visit ICTS and give lectures there, and then it's a great pleasure to be here too. So let me share my screen, and I believe I should be able to show this like that now. Can you all see my screen now?
Yes.
Okay,
we can see your screen and hear you clearly.
Okay, and you can also see my mouse, presumably, right?
Yes.
Okay, great. So again, thank you so much for inviting me to talk here. And it's really a great pleasure to say a few words about the legacy of Ivan Choquet-Bruhat. Okay, and I struggled a little bit about how to name this talk, but given that the conference is called Predictability in General Relativity, and since I'll make some connections to numerical relativity, I thought predictability in numerical relativity would just hit the right tone. Actually, maybe I should share how I first learned about the name Ivan Choquet-Bruhat. That was in the early 90s when I was a student. And I was a fellow student who basically carried around this book. Not quite at all times. I think I'm exaggerating a little bit, but they had almost something religious about it. And basically, this book was what he charmingly referred to as the three women book. It's this analysis, manifolds, and physics. And so I always held Ivan Choquet-Bruhat and her work in very high esteem. Now, that was, again, in the early 90s, when actually just around the time when she retired. Okay? And preparing for this talk, or basically even since then, I realized that she wrote several more books. So preparing for this talk, I thought I'd go to Amazon and just look for books by Ivan Choquet-Bruhat. Okay, and now I realized what I wanted to say is that I apologize for this. That really, given that I've basically had such high esteem for her work for so many years, really, I feel it's a great honor that I have to have this opportunity to say happy birthday. So happy birthday. It is a great pleasure to say to be part of the celebration. And again, as I prepared for this, I looked for several books, and it's really remarkable how many books Yvonne Choquet-Bruhat has written and how much influence she clearly had on the field. Okay, so even after the retirement, even in recent years, there were new books, textbooks on general relativity, on fluid dynamics and other things. So a very impressive body of work. Now, I'm not going to judge as to what her most influential paper is, but one paper that certainly comes to my mind is this paper from 1952, the existence theorems for certain systems of partial differential equations, the nonlinear partial differential equations. Before I go on, I should actually say a couple of things. One is that because of the time zone, I'm actually currently in Arizona, so it's almost 12 hours away. So because of that, I have not been able to listen to the previous talk. So my guess is I may repeat some things that other people have already said. I apologize for that. I will also apologize for, in my overview of lots of different work, that I'm sure I will miss some references, and I apologize again for doing that. It's certainly not on purpose. And also, I will go through some technical things. Please feel free to interrupt me at any time and ask any questions as they come along. So here then is an outline of what I want to talk about. I will take this 1952 paper that I just mentioned as a starting point, and using that as a starting point, I will actually point out how profound the influence on that paper had on a lot of the work in numerical relativity. And I'll actually trace some of these developments in two of the formulations that are very commonly used these days, namely the generalized harmonic formulation and what I will loosely refer to as the BSSN formulation, and various different modifications of that, including the Z4 formalism and others. Now, a lot of this work in the context of the 1952 paper relied on harmonic coordinates. And then I'll make the point that those harmonic coordinates may or may not be useful for numerical experiments or numerical work, where basically, for example, we may want to model black holes. And so we may want to maintain the coordinate freedom to use coordinates that are well suited for those purposes. And so that introduces different kinds of coordinates. And basically, I could then, review some of these triumphs of numerical relativity in black hole simulations and all of that. But rather, actually, for the purpose of this talk, I thought it would be neat to highlight how we can use analytical work to get insight into how some of these gauge conditions work and how some of these conditions lead to qualitative differences. So basically to highlight how basically numerical relativity, numerical simulation, in my mind, certainly has greatly benefited from analytical analysis. So basically I would like to highlight how I think it's very fruitful to look at the complementary strengths of both numerical and analytical work. Of course, you could also argue, I'm just going to talk about some topics that basically have satisfied my personal curiosity in how some of these things work and some of these things that we see and observe in numerical simulations. But coming back to this 1952 paper, essentially this paper has two parts. In the first part, Yvonne Choquet-Bruhat demonstrates the existence of solutions to these nonlinear second-order differential equations. And here's basically the starting point are these type of operators and equations where basically they're second derivatives with various different functions and they're decorating these second derivatives. And this existence theorems basically resulted in the notion of predictability, and that explains why the word predictability is in the title of this conference. Now, this is already, of course, a remarkable result. From the perspective of general relativity, it's particularly remarkable, of course, because we know that we can cast Einstein's equations in precisely this form. And just to basically review why that is, I will remind people that we can write the Ricci tensor in basically three different ways. Okay? The first ways are certainly, I think in many general relativity courses, the first way we learn about it is to write the Ricci tensor in terms of partial derivatives of the Christoffel symbols. Personally, actually, I think this is probably the least useful way of writing the Ricci tensor, but it's probably also a matter of taste. Another way of writing the Ricci tensor is to write the Ricci tensor in terms of second derivatives of the metric. And if we do this, there are 4 terms. I already put down 2 here because the other ones didn't fit into this line. But the first one you see is kind of a nice operator because it is actually of the form of what we just saw in this differential operator in Madame Choquet-Bruhat's paper. Okay? So basically, this one looks like a wave operator, if you want to, in 4 dimensions. We're contracting over the gamma and delta here. So basically, it's like a wave operator acting on the metric. And then these other 3 second derivative terms have the indices all mixed up in various different ways. Now, the third way of writing the Ricci tensor is recognizing that these mixed second derivatives can also be combined into terms in which we take a first derivative of these contractions of the Christoffel symbols, which we can also write as partial derivatives of the metric if we decorate it with the determinant of the metric. Okay? Now, using the gauge freedom, the 4-dimensional gauge freedom, at least in 4 dimensions, dimensional spacetimes, we also recognize that we can use the gauge freedom to set these gammas to 0, in which case the principal operator that is left over are just these second derivatives. So by doing that, we've reduced the problem to exactly the form of the equations that were the starting point for this paper. Okay? And that's exactly the point here. So basically back then, these coordinates were sometimes referred to as isothermal coordinates. We now refer to them as harmonic coordinates. But the idea is that we take precisely these terms, we set them to 0. Here's the Einstein's equation in terms of the Ricci tensor. Okay, here the second derivatives plus nonlinear terms. And these L's, which have the partial derivatives of these F's, these terms we can now set to 0 by setting the F's to 0. And that means we have now cast Einstein's equations precisely in the form for which Ivan Choquet-Bruhat proved the existence, and that provides us with predictability in general relativity, hence the name of this conference. So that is a beautiful result. And again, I will trace how basically this notion had a huge impact on these different formulations in numerical relativity. Now, the fact that Einstein's equations can be written in this form using harmonic coordinates actually goes back. Actually, it goes back to the year Ivan Choquet-Bruhat was born in the early 20s. Okay, actually, Einstein, I think, used it even before finally in general relativity. Actually, one thing that I find remarkable and really neat as preparing for this talk is that many of these original papers you can find on the internet. Can find on the internet. So this is, for example, this paper by Lanchos looks like. Okay, the Originalmitteilung in der Physikalische Zeitschrift from 1922. And we can zoom in a little bit and you see that those are exactly these terms that basically we set to 0 early, these partial derivatives of the metric, okay, which we can also write in terms of the Christoffel symbol. So that was all known. Okay, but as I said earlier, or mentioned earlier, is these harmonic coordinates, or isothermal coordinates, as they were called then, are not necessarily useful in numerical relativity. Again, that is, I'll go into more detail later, but that is in large part because it doesn't, by using those coordinates, we would have already used the gauge freedom, so we no longer have the gauge freedom to choose coordinates that may be well suited to model black holes, for example. Therefore, there was interest in basically generalizing these coordinate systems. And one step in doing this is to not set these gammas that we've introduced before to 0, but maybe to equate them to what they're called gauge source functions. So basically, rather than setting them to 0, we said, well, there's some functions for which we will have to make choices that are given as functions of the coordinates. Okay, so this is a few lines taken from this 1985 paper by Helmut Friedrich, where he does exactly the same thing. Here the gammas, here is the Ricci tensor written in terms of these terms. So basically we see that's exactly the same form. The difference now is that we do not set these gammas to 0, we equate them to some gauge source functions. That's precisely the form that was adopted by Franz Pretorius in his way of writing what he referred to as the generalized harmonic formulation. There are other pieces that went into that. There's some constraint damping terms that I think are due to David Garfinkel, some other authors. I think Carsten Gundlach made some contributions. This is also related to the Z4 formalism that was proposed by Bona and his collaborators. But basically, many of these ideas enter into the generalized harmonic formulation. And again, here's the form of the equations precisely with these second derivatives of the metric, and then basically these H's, these gauge source functions for which we have to make choices. That is the formulation that Franz Pretorius used for his beautiful first successful simulations of binary black hole mergers. And here's some snapshots of these mergers, which go back to 2005, almost 20 years ago, which is remarkable. So these were these first successful simulations that we celebrated back then. All of this, what I told you about, is a second order formulation. For some numerical simulations, it's also it's a good idea to actually use first order formulations. There's a paper by Lee Lindblom that it does exactly that. It starts with a second order formulation, which by now you recognize. Here are the second derivatives of the metric. The metric is written as psi here. Here are the first derivatives of these new variables gamma. So it's this exact same idea. We may all take a wild guess what this reference 5 is. It, of course, refers to Yvonne Choquet-Bruha's paper. Okay? This leads to a first order simulation, which, you know, these are the equations. Not particularly pretty, if you ask me, but that's not the point. These equations were then used in the as a foundation of the spectral Einstein code spec, which was used for many numerical relativity simulations, I believe, for example, for these beautiful results in the discovery paper of the first gravitational wave. So it's neat to see how actually Yvonne Choquet-Bruha's influence from the 1952 paper traced exactly into all these formulations that then produced these numerical relativity results. So this was in the context of the generalized harmonic formulation. You could also ask what does this have to do with the BSSN formulation? Works a little bit differently. Now I put BSSN in quotation marks. This formulation really goes back to Nakamura, Obara, and Kojima in 1987. Then Shibata and Nakamura used it in the mid-90s, and Stu, Shapiro, and I basically, if you want to just put some finishing touches on this. The idea is that you start with a 3+1 decomposition, often referred to as the ADM decomposition or formulation. In terms of this decomposition, we can write the metric in this form, where alpha is now the lapse function, gamma ij is the spatial metric, and beta is a shift vector. The idea is that you then use a conformal decomposition of the spatial metric, write it in this way. And now the key idea is that everything that we previously said about the Ricci tensor, about the four-dimensional Ricci tensor, we can now apply to the conformal spatial Ricci tensor. We can again introduce gamma i's in exactly the same way as before. The beauty now is that by having done the conformal decomposition, we are free to choose the determinant of the conformity-related metric. We can set it to 1. That means these determinant terms that we previously had in the partial derivative exactly cancel out. And then we can write the spatial Ricci tensor in exactly the same form as before. Here are the second derivative terms. Here are the derivatives of these new, what we now call the connection functions gamma, and then they're nonlinear terms. So this is taken from Stu's and my paper. So you see that it's again, exactly the same idea. It traces back exactly to the same arguments as before. This is a little paragraph out of Stu's and my paper, where indeed we motivate this approach exactly by referring to the symmetric hyperbolic form proposed in reference 24, and you may all take a guess as to what reference 24 is. So even in the BSSN formulation, which is really uses it 3+1 decomposition, then rather than starting with the space-time equations, basically it's the exact same arguments that bring the equation to the form. So really they're all very similar. One difference here is that rather than using gauge source functions to impose the gauge or choose the gauge, in other words, rather than making choices for these gammas, we now derive an evolution equation for gamma. And basically, we can then impose the gauge by making choices for the lapse function alpha and the shift vector beta, okay? And basically using those lapse functions in shift vector, those then basically enter on the right-hand side of all the equations, including the equation for the gammas. So basically these gammas are now, these connection functions, gamma I, are now considered independent functions on the same footing as the conformally related metric, the extrinsic curvature, and the other quantities. Okay. Here's one example where Stu and this presentation is not exactly in chronological order. This actually predates these binary black hole simulations. This is where we, I think, demonstrated for the first time the advantages of this formulation. So this is a plot for a component of the extrinsic curvature as a function of time, evaluated at the center of the coordinate system for just a weak gravitational wave. But you see that the original, what we refer to as system one, the original formulation is the ADM formulation. The code crashes after a certain time. You see this dashed line, whereas the solid line is the result using this reformulated equation, what now people refer to as VSSN, and it's much more stable. It actually ran forever. It works well. This example is done with harmonic slicing, which is a little bit different from harmonic coordinates in the sense that in harmonic slicing, we set only the time component of this four-dimensional gamma vector to 0. Okay? And we also set the shift to 0. So it's a little bit different. It's not quite the same as harmonic coordinates. It only basically uses the t component of the harmonic coordinates. And now we come into the part where I'll talk about generalizations of these harmonic coordinates as well as harmonic slicing. And I'll discuss basically how those were used to perform simulations, for example, of black holes. Now, I just told you what harmonic slicing is. It is basically, we can write it by setting just the time component of these four-dimensional connection functions, if you want, to 0. If we wrote out this equation, we can also write it in this form. So based on the left-hand side, it's just the derivative of the lapse along the normal vector, if you want. So that's what this is. And on the right-hand side, it's the lapse squared times the mean curvature k, i.e. the trace of the extrinsic curvature kij. And now Bona, Masso, and their collaborators basically had a very good suggestion. They said, well, why don't we generalize this coordinate condition by inserting a function f of alpha. And now we could think about what might be a good choice for this function f of alpha. We could also think about some examples. For example, geodesic slicing we obtain just by setting f equals to 0. Evidently, if we choose f of alpha equals 1, we get back harmonic slicing. It's the same thing as here. Back in those days, maximal slicing was a very popular choice, and maximal because it had the demonstrated property of avoiding singularities. Maximal slicing refers to k equals 0, and formally, if you think about this, is basically let's assume the left-hand side remains non-zero. Then if k is 0, the only way you could achieve that is if f actually goes to infinity as the lapse goes to 0, as we're approaching a singularity. And we can kind of mimic that by making a choice for the function f that goes to infinity as alpha goes to 0. And one choice for that has that property is choosing f of alpha to be 2 divided by alpha. This is now referred to as the 1 plus log slicing condition, because we can show that under certain circumstances, in that case, the determinant of the metric, the lapse just takes the form 1 plus log of the determinant of the metric. People started using this function in the early 2000s or mid 2000s, and basically just after Franz Pretorius had presented his results to other groups independently, namely the group around Manuela Campanelli and around John Baker, it performed simulations of binary black holes using this 1 plus log slicing condition, and it worked like magic. It's basically, they were able to follow this complete in spiral, they followed the horizons, and they were able to extract gravitational waves. It was a beautiful result. The unsettling question is, but why the heck does this work? What happened to the black hole singularities? I mean, basically, why can you just use this condition without using excision or doing anything else to deal with the singularities? Why does it just work out of the box? It's like magic, okay? And basically what I would like to talk about is how can we understand why does this work? So in the next section of this talk, I will explore analytically, why is it that this 1 plus log slicing works for black holes? And what I'll do is I followed basic papers by Mark Hanam et al., who at the time was in Jena. And so he worked with his collaborators there. There's Sasha Husa, Bern Brookman, Neil Ormudu, who came from Cork, visited, and they had exactly the right idea, namely, well, if we want to understand this, why don't we study these 1 plus log slices for virtual spacetimes? And more precisely, they studied static 1+ log slices and found basically what slices do we asymptote to if we do numerical simulations of black holes using this 1+ log condition. The technique that they used for this, which I'll go through, adopts height functions. So the idea is the following. Let's start with the Schwarzschild metric, maybe in the form that we are all used to it, where F is just a shorthand notation for 1 minus 2m over big R. R is the area radius. And I use T bar as the normal Schwarzschild time here just to avoid clutter later on. Okay? And now we'll introduce a height function, h of r, which is sketched here. So basically here, the blue line is a line of constant Schwarzschild time, but maybe we want to consider a new slicing that corresponds to a new time t equals constant. And in order to construct the slicing, we have to lift the slicing out of the slice by a certain height function, h of r. So using this transformation, we can see what form does this metric take in these new unbarred coordinates. And if you go through, basically do these partial derivatives, you get this expression. What we'll do next is we'll compare this form of the Schwarzschild metric with the 3+1 form of the metric, which I had written down earlier. So here's the 3+1, the ADM metric. This is what we just found from this transformation using the height function. And we can now identify corresponding pieces. So for example, this gamma RR, the component of the spatial metric must be this term, so that must be this. And we can do a similar identification for the shift vector and the lapse function, and we get these expressions. Okay, so again, the bottom line here is that we get expressions for the lapse, shift, and spatial metric by identifying the transformed Schwarzschild metric with the 3+1 metric. And not surprisingly, these terms will now include the derivatives of the radial derivatives of this height function h. Okay. Next, what we want to do is we want to not just construct any slice, we want to construct a slice that satisfies the 1+ log slicing condition, i.e. the Bonamasso equation with this choice f of alpha equals 2 divided by alpha. That equation involved the mean curvature on the right-hand side, which we can now compute. We can, as a starting point, we realize that the mean curvature is the same as the trace, a divergence of the normal vector. We can use similar identities as we saw before, and basically we can then write this in terms of the shift and the lapse in this compact form. Now, one key property that we have for the spatial is for the static slice, and I'll go back to my previous slide for just a second here. One key property here is that we can express the shift and also the spatial metric in terms of the lapse. So basically we can eliminate the h primes and write everything as the lapse. In terms of the lapse, that allows us to basically integrate this static Bonamasso equation, and we get an expression for the lapse that takes this form, where the c is now a constant of integration. Now, your next question should be, well, great, but how do we choose this constant of integration? And it turns out we cannot choose it arbitrarily, because for arbitrary c, these slices would not extend into the black hole. But we want to model black holes, so we want slices that extend into the black hole. And so in other words, slices whose end is inside the black hole horizon. And in order to do that, or to see how we then have to choose this constant c appropriately, it turns out that we can write all of these equations as an ODE for the lapse alone. Okay? And this is this beautiful realization that came out of this Hanam et al. Paper. This equation for the lapse takes this form. Okay, and the key point here is it's a ratio. There is a numerator and a denominator. And it turns out that the denominator has a 0, it has a root at some point, which I'll call the critical radius RC, which is inside the horizon, okay? This root exists for positive lapse, okay? So what that means is, if we want the lapse to remain regular at that critical point, then we have to make sure that the numerator vanishes at the same point, so that these two, basically, we have 0 simultaneous roots in the numerator and the denominator, and that allows us to construct regular solutions for the lapse, which go both into the black hole and then vanish at some root for the lapse inside the black holes, which then defines the endpoint of these slices. Now that requirement that we have simultaneous roots here, that singles out a particular C for the desired solution, given that this equation that I just wrote in the previous slides is already this transcendental equation. So basically this involves sometimes solving quartic equations. So it's not particularly pretty, and why I won't go into that. But the point is we can do that. So now we've identified a certain value for C. Now this lapse remains regular all the way to a point at which it vanishes, a root of the lapse. And that point I'll call R0. Okay. So basically R0 is greater than 0, but it's smaller than this critical value RC, or greater or equals, and both of them lie inside the horizon. I can do one more thing. I can expand the lapse about R0, which gives me a coefficient A1. In other words, in the neighborhood of the endpoint R0, I can write the lapse alpha as the A1 times R minus R0 plus terms that are then quadratic R minus R0. So there's a regular expansion of the lapse about this endpoint R0. We can do one more step. We can now transform this into isotropic coordinates. Okay, automatically because gamma R diverges at this R0, the center of these isotropic coordinates, which I'll call little r, will correspond to the endpoint of the slice at capital R equals R0. Okay, so basically we could go through the math, but maybe you can just take my word for this for now. Basically, we can do this transformation to isotropic coordinates in which the spatial metric will take the form of a conformal factor times the flat metric. And the flat metric is now written in terms of this isotropic radius little r. And as a key property of these slices that you find this way is that the conformal factor will scale with the inverse of the root of this little r. And that will be a key property of these slices. Now, your question now should be, well, what the heck is special about these slices? Okay, they all start in a Penrose diagram. They all start at spatial infinity, as many of the other slices that we may be familiar with. Okay? But what's different now is that they end at a certain point R0, which I've told you before is greater than 0. Actually, they asymptote to these slices. These are also less than 2m, so they're inside the black hole. And these dotted lines in here are lines of constant areal radius inside the black hole horizons. So all of these lines, they asymptote to a certain value of these constant areal radius. What that means is that they actually never touch the singularity at r equals 0. So these slices never reach the curvature singularity. So if we use these coordinates, and if our simulations settle down to these particular slices, those slices will not touch the curvature singularity. We avoid the curvature singularity just by choice of these coordinates. Okay? Now, I told you that conformal factor goes with the isotropic radius to the minus 1/2, okay? So certainly we do have a coordinate singularity at little r equals 0, and you could worry that this coordinate singularity will bother our numerical simulations, but it also turns out that this coordinate singularity is an infinite distance away from any point inside the slice. How can we see that? Well, we can measure the proper distance by integrating from 0 to, let's say, a little epsilon, gamma r to the 1/2, but gamma r will go with psi to the psi squared, but psi squared will go with 1 over r. So this gives us a logarithmic divergence, and we see that any point at even a radius epsilon, as long as epsilon is just greater than 0, any spatial point will be an infinite distance away from the coordinate singularity at little r equals 0. If we represented this in an embedding diagram, these slices would take this form. They asymptote to a constant area radius, a cylinder if you want. And because of this form, basically Hanam and his collaborators called these slices trumpet slices. So these are these famous trumpet slices, which now play a very important role in numerical relativity simulations of black holes. Okay. And the properties of these trumpet slices, in a nutshell, they asymptote to this infinite cylinder, which is typically spelled with an I notice here, okay? But they do not reach the space-time singularity, and that's why they allow us to do these simulations. Now, what I sketched is a derivation for one particular form of these trumpet slices, but there's many ways of slicing Schwarzschild, just like there's many ways of slicing the pie. Here's another way. Here's a whole family of analytical trumpet slices of Schwarzschild that my collaborator Ken Dennison came up with. There's a whole family of these. These families are parametrized by the endpoint of the slice, which we called R0. Okay. Now, what is really neat is that if you one endpoint of this, one member of this family is R0 equals 0, in which case we get Parnley-Goldstrand, the well-known Parnley-Goldstrand coordinates of Schwarzschild. But for all values R0 greater than 0, actually these represent a trumpet geometry. My favorite member of this family is R0 equals M, because in that case, this F1 just reduces to M, everything simplifies, and we actually get a remarkably simple solution for the Schwarzschild geometry, in which the labs, shift, and conformal factor just take this form. And again, I think this is a beautiful way of writing Schwarzschild. It's not my favorite. Okay, of course, I'm biased. It has some really neat properties. The area radius R is just the isotropic radius plus M. Okay, in particular, you see that the origin, little r equals 0, corresponds to big R, the area radius equals M. So we see immediately, well, it does not reach the curvature singularity. These are horizon penetrating coordinates, i.e. they remain perfectly regular on the horizon. They're also isotropic, by which I mean that the spatial metric is just this conformal factor to the 4th power times the flat metric. It is easy to verify the trumpet properties. In particular, you notice immediately that the conformal factor goes with 1 to the r to the minus 1/2 as little r goes to 0. And it also satisfies the Bonner-Master slicing condition with a specific choice of this function f of alpha. So I think this is a really neat way of writing analytically a trumpet geometry that allows us to explore the properties of these trumpet geometries for a very simple example. Now, your next question might be, well, that is all fine and well. Is there any guarantee that 1 plus log slicing will always work? And always, of course, is a big word. I don't think anybody would want to write a blank check and say it will always work. Okay, but here's an example. Okay, one application for numerical relativity many of us are interested in is critical collapse or critical phenomena in gravitational collapse. Okay? And those critical phenomena were first announced about 30 years ago by Matt Shoptwig in this beautiful paper in which he considered scalar fields and spherical symmetry and discovered all these remarkable properties as you fine-tune initial data to the onset of black hole formation. Very shortly after this, just months later, two colleagues, Andrew Abrahams and Chuck Evans, found very similar phenomena in the case axisymmetric simulations of vacuum gravitation collapse, i.e. basically set up nonlinear initial data describing vacuum spacetimes, i.e. nonlinear gravitational waves, fine-tune those to the onset of black hole formation and see what happens. And what they found is phenomena that are very similar to what Matt Shoptwig found. So that kind of set the expectation that, well, it always works the same way, and there's always a very similar critical exponent, and is truly remarkable behavior. It was also a really neat paper, and I recommend taking a look if you haven't done that already. One problem with this paper is that for many years it remained very difficult to reproduce this. And this is just one example of a plot in the paper that David Hilditch and myself and several other collaborators. This is the mean curvature as a function of space at various different times. And you see that at a certain finite time, there's this spike that develops. It seems to basically produce a coordinate singularity, and that actually prevented us from doing simulations of, a fine-tuning to this critical onset. Now, it took me, I'd say, a somewhat embarrassing amount of time to realize that this might have something to do with a paper that Miguel Alcubierre wrote in the late 90s, in which he predicted that, well, if you use 1 plus log slicing, there might be coordinate shocks, okay? And in fact, that is exactly what we found in this critical collapse simulations of gravitational waves, okay? And the beautiful thing is that Miguel Alcubierre also had a suggestion for how to fix it. Namely, he suggests, well, if rather than using this 2 over alpha for this function f of alpha. Why don't you try 1 plus kappa divided by alpha squared? And he had a gauge shock test in which he demonstrated that. Here's a reproduction of these shock tests that David Hilditch and I did. And what you see here is, so basically it's actually flat space. You just start out with a little gauge wave, and after a finite amount of time, 1 plus log slicing will lead to this steep gradient developing in the labs, which also corresponds to this spike in the mean curvature, which looks very similar to what I just showed you from these critical collapse simulations. On the other hand, if you use this shock avoiding slicing condition with different choices for this kappa, you see that these, in this case, everything remains just fine. So that then encourages us to try out this shock avoiding slicing condition for critical collapse, and indeed that allowed us to do it. It worked beautifully. Here's in the top panel, I show you the labs evaluated at the center at the function of time. The green dashed line shows you the 1 plus log slicing result, and here the code crashes after a certain amount of time. Whereas if we use shock avoiding slicing, you find these oscillations and all as well. Okay, here in this plot, this is similar to what I showed you earlier. This shows you the mean curvature at a certain moment in time, just before this 1 plus log slicing case crashes. And this is shown now not as a function of time, but rather as a function of along the z-axis. And you again see a feature developing here, which shortly afterwards would become a big spike, and it leads to the code crashing. So this now allows us to do these simulations of critical collapse. And this would be a beautiful segue. It would be tempting to talk about critical collapse now, but I will not do that. Rather, I'll tell you a little bit more about the properties of these shock avoiding slices. One of them you already see in this plot. Namely, you notice that, wait, the lapse becomes negative here. Okay, so there's moments in these evolutions when the lapse becomes negative. Miguel Alcubierre already anticipated that in his 1997 paper. He saw that he argued, but look, if we allow f, if we replace f with this function, then it will become alpha squared plus kappa. So as alpha goes to 0, this equation does not guarantee that the derivative of the lapse also goes to 0. So it can go right through 0 and become negative. And that's precisely what we find in these simulations. And that is somewhat disturbing for those of us who grew up with the notion that a 3+1 decomposition is based on a global foliation. Clearly, these slices do not form a global foliation anymore. On the other hand, does it really matter? Because in this case, the code worked just fine. So a couple of years ago, or a year and a half ago, David Hilditch and I decided to perform a whole bunch of tests where we took basic textbook cases and just evolved them with 1 plus log slicing and these shock avoiding slicing and compared them. So here, for example, is Schwarzschild. In the top panel, I'm showing you the coordinate location of the horizon as a function of time. And you see that there's lots more wiggle going on if we use the shock avoiding slicing in comparison to the 1 plus log slicing. But if we look at gauge invariant quantities, for example, the horizon mass, and here I'm plotting the difference of the actual numerical horizon mass from what it's supposed to be, and you see that these differences are all very similar. And if anything, actually for kappa equals 1, the error is a little bit less than for 1 plus log slicing, okay? We don't see the code crashing or anything. So in terms of accuracy, stability, they behave very similarly. We did this also for Kerr. The result is very similar. Basically, if we look at coordinate quantities, there's more wiggle, there's more oscillations. But if we look at gauge invariant quantities like the masses of the horizons or proper circumferences along the equator or across the pole, then all of these behave very similarly. Here's a head-on collision of two black holes, so spacetimes that are actually dynamical. Again, this is the lapse. So this is basically, it shows more coordinate dynamics, but in terms of invariant quantities, it's again very similar. You again see that the lapse definitely becomes negative. Okay, so we've done many of these simulations, and again, basically, we don't see any big difference in terms of accuracy or stability. Okay, let me go back to the Schwarzschild case. So in this particular, admittedly messy plot, What I'm showing you is the lapse at the center of the simulation as a function of time for a simulation in which we start out with a so-called, wormhole geometry. In other words, where the conformal factor is 1 minus m divided by 2r. So this is what you get for isotropic coordinates on a slice of constant Schwarzschild time. But now we evolve this with a Bonner-Maso condition for these two different choices of f of alpha, as I said before. And it's a little bit difficult to see here, but for the 1 plus log slicing, for the solid blue line, it starts out at 0. We then get an onset of a coordinate transition. But then, basically, this transition, it becomes non-zero, but then it settles down. And it seems to approach 0 more or less exponentially. With a little bit of goodwill, you can, it's more or less exponential, okay? So that's what I wrote down here. That's what you find for 1 plus log slicing. On the other hand, if we do this with shock avoiding slicing, then we get these wild oscillations. And even at late times, basically, these oscillations don't really seem to die down, okay? And, it doesn't take too much convincing to interpret this as a harmonic oscillation. And now this is a kind of a puzzle, because why the heck is that? Okay, so basically we do the exact same simulations. The only difference is that in one case we have f equals 2 divided by alpha. In the other case, we make this choice for this function f. But it's the same equations, but we see qualitatively different behavior. In one case, we find exponential decay for the lapse, which really is like the smoking gun of a first order ODE. Whereas in the other case, we see harmonic oscillation, which we've all learned is kind of, that is what you get if we are dealing with a second order ODE. So why is there this qualitative difference just depending on what choice of F we make in this case? And the last few, basically for the rest of my talk, I just want to explain how we can understand that. And I think, again, maybe this just satisfies my personal curiosity, but why is it that there's this qualitative difference? And in order to study that, it looked at a perturbative time-dependent height function approach in the vicinity of the puncture to figure out what is it that causes to this, what leads to this qualitative difference, okay? So again, let's basically return to a slide similar to what I showed you before. So we again use a height function to describe a coordinate transformation from the Schwarzschild slice to some arbitrary slice. Or we will make a specific choice, but for now it's arbitrary. The only difference from before is that I now allow this height function to be an explicit function of t. So h is now a function of t. Now remember what we did before. We transformed the Schwarzschild metric using this height function, okay? And that introduced derivatives of h. When we did this before, we only encountered spatial or radial derivatives of h because h was independent of t. But if h now depends on t, you won't be shocked to hear that when we now identify the lapse, the shift in the spatial metric, these expressions will also include the time derivative of h, which I denote with an h dot here, okay?
Sorry, Professor Wersker had a question, so
please go ahead.
No, I can ask it then. Thomas, please go on.
Okay.
I'll ask it then.
Okay, sure. I'm happy to answer it now, but anyway, either way, I'm perfectly fine, okay? But basically, one big difference from the static case that we talked about before is that in this case, we can no longer express the shift and the spatial metric in terms of alpha. Remember, that was one of the key ingredients that allowed us to do this beautiful analysis before. Now we can no longer do that. Okay, so basically, we have to kind of go to plan B, and maybe our plan B is to say, well, tell you what, maybe we won't do this exactly in a nonlinear case. Maybe what we'll do is we'll adopt a perturbative approach in which we write this time-dependent height function as the static height function that we used before, okay, plus a little perturbation, which I'll call eta, and this perturbation is now allowed to depend on t. Okay, so fine, that sounds like a fine idea, but there's a but. Okay, now what is the but? And the but is, well, I have to be, I told you the truth, but maybe not the whole truth, because when I drew these kind of sketches, I kind of pretended that h is a well-behaved function and it looks pretty everywhere. That actually is not really so. Okay, so in the reality, this, for example, is h, what you get for this analytic solution that I showed you earlier. Okay, now, and you see that it diverges. It diverges at 2 points, and it's easy to see why that has to be, because if you remember this, for the static height function, I'm sure you don't remember this, but we could go back in the slides and we could see that in that case, we identified the labs from this function f, which was just 1 minus 2m of r, divided by 1 minus f squared, h prime squared. That's what we found for the identification of the labs. Now, at the endpoint of the labs, okay, at r, what I call it R0, we want the labs, or we know that the labs is 0 there, but f is non-zero there. So the only way how we can get 0 labs for a non-zero f is by having h prime diverge at that point. That's why we get this divergence of h at that point. The opposite applies actually at the black hole horizon. At the black hole horizon, f is 0, but alpha is non-zero. And again, that only works if h has a divergence there, okay? So fine, that is okay, all right? But the problem is now that our naive perturbation, of course, we can use in a region, for example, out here, as I'm sketching here, okay? But we cannot use this type of a perturbation around a singularity. So how can we then use a perturbative approach around the singularity? Well, we can do that, but we have to use a different idea, a different way of writing the perturbation. And what we'll do is we basically perturb in the radius. We say, okay, the time-dependent height function that we now consider in the vicinity of this puncture of where the static lapse goes to 0, we'll write as the original function h0, but evaluated at a slightly different r. I'll call this r bar, and this r bar is really our original r plus a little perturbation rho that shifts the singularity around. So we write it this way. Okay. Now, remember, when we now want to construct the metric, we have to do the perturbation. We use the coordinate transformation. Actually, let me just go back a few slides. You remember that this involved both space and time derivatives. So now we need to evaluate these derivatives using this approach for this perturbation. And the time derivative, for example, we would take by saying, okay, it's the space derivative h0 times the time derivative rho with the derivative of rho with respect to time. I'm sorry about that. Likewise, basically, oops, this is a typo. I apologize. This should be an h prime. Okay, this h prime is now h0 prime evaluated at r bar times 1 plus rho prime. So we can evaluate these derivatives. We can and then insert them into the labs to shift in the spatial metric. I'll just give you one example here. This is the expression for the labs. And again, there's both time derivatives and space derivatives. What we'll do, and basically you do this and it will still be very messy, okay? And too messy to actually make progress in general. So what we'll do is we'll focus now only on the puncture. And remember, the puncture is now defined by the place at which h prime goes to infinity. We've seen that that's exactly the endpoint of the metric. So we now focus on the endpoint of the metric by letting h prime 0 go to infinity. That will, once we do that, we see that basically only this term and this term down here will survive. And in this case, alpha just becomes rho dot divided by 1 plus rho prime times the factor of these f's. And again, f is just 1 plus 2m over r. Okay, so far so good. Okay, now we want to again construct the Bonner-Masso slicing of the space-time, and in order to do that, it is useful to recognize that I can define a new time operator, a time derivative, which is the derivative along the normal vector, which is also, if you want to, the advective derivative along the puncture itself. And we can write, we can write that as partial t minus beta r partial r. And if it turns out that I can then write the labs, for example, as this prefactor times just partial n rho. So this is neat. Basically, it turns out these equations or expressions simplify quite a bit if we evaluate them at the puncture in terms of this advective time derivative. And then we can actually construct the Bonner-Masso condition. On the left-hand side, we have this operator that we had all along. Now the labs, basically, I can write in terms of this. This is already just partial n, so the left-hand side becomes this operator. On the right-hand side, we basically have the external curvature, which we now have to evaluate at this r bar, and I'll do that by evaluating it at the original r0, the original location of the puncture minus a rho times k prime. And my key point now is that the behavior, okay, okay, actually, before I say this, you notice this is already an ODE in N. So basically, by having gone to the puncture, basically the differential equation at the puncture already decouples from the rest of the equations, and we end up with an ODE that governs the behavior at the puncture itself. Okay. Now, the nature of this equation depends on what K is at the puncture. So let's take one more detour before we can evaluate this and talk about what is the value of the mean curvature at the puncture. We can figure that out. There's different ways of doing this. One way is to go back to the Bonner-Masse equation. Remember, the Bonner-Masse equation had the mean curvature K on the right-hand side. On the left-hand side, we had the partial derivatives of alpha, but for static slices, the time derivative is 0. We only end up with this term, and we have to divide by an alpha squared f of alpha. Okay. Now, I can write this in term, I can replace the shift at the puncture just in terms of this f term. We end up with only this one. And also, many slides ago, I introduced the value of the derivative of the labs, i.e. the first term in the Taylor expansion of the labs as an A1, and that was some finite non-zero value. And now you notice that the value of K will depend a lot on what f is. If f is 2 over alpha for 1 plus log slicing, then this term just becomes 2. And now we have some finite term divided by 2. And actually for 1 plus log slicing, this happens to be 0.301 in units of the black hole mass M. However, things are different for the shock avoiding slice, because now I insert f of alpha equals this. As we let alpha go to 0 close to the puncture, this term will dominate. I get one factor of alpha upstairs, and you see that this term goes to 0. So this is a qualitative difference, which results from the value of the mean curvature of the unperturbed trumpet slice. Okay, there's something. The trumpet slices for shock avoiding slices have very special properties. In some ways, they're much nicer than for 1 plus log slice because everything is analytical. You can do it all analytically. One result is that the mean curvature at the puncture itself vanishes. And now that leads to a qualitative difference in the behavior. Let's first talk about 1 plus log slicing. For 1 plus log slicing, this term is non-zero. That means that to leading order, we can ignore the second term, okay? But if we ignore the second term, if this term is gone, then you notice that rho itself makes no appearance in this equation. It is only the derivatives of rho, which are also hidden in this alpha. So that means I can write the whole thing in terms of either the first derivatives of rho, or I can replace them again of alpha, and that I end up with a first order ODE for alpha, which is just partial n alpha equals minus 2 alpha k. Okay, with k a given value of the mean curvature at the puncture. This, of course, we can integrate immediately, and guess what? We get exponential decay exactly as we observed in the numerical simulations. And when I say exactly, I don't mean exactly as in exactly quantitative agreement, because there's some quantitative difference that come from certain assumptions and also from the difficulty of actually evaluating these quantities right at a curvature singularity. Nevertheless, qualitatively, this predicts exactly what we observe in the numerical simulation. So that's nice. Okay. How about shock avoiding slicing? Now, in shock avoiding slicing, we start with the exact same equation, but the key difference now is that this k is 0. So we can no longer ignore this term. In fact, this term is now the leading order term on the right-hand side. But that means that rho no longer disappears from the equation. Rho itself now remains in the equation. So we cannot write in everything in terms of the labs. This is truly now an equation for rho. And in particular, what that means is the left-hand side remains a second order operator acting on rho equal to a rho on the right-hand side, which to linear order we can write this way. Okay, and now you notice, oh boy, this is exactly a harmonic oscillator equation. We can even figure out, we can compute what is the frequency that we expect from this ODE. It turns out to be proportional with kappa, which is exactly what we found before. So the bottom line here is that this gives us analytical insights into why it is that 1 plus log and shock avoiding slicing behave so differently. We can even make predictions for the qualitative behavior. We see that 1 plus log slicing gives us this exponential decay, and this allows us to predict even that basically, yes, for shock avoiding slices, you should see these harmonic oscillations. You can even make predictions for these oscillation frequencies. Okay. So what I went through, and I hope I didn't overwhelm you too much with all these details and equations, but the bottom line is that we do lots of numerical simulations, and these simulations give us lots of different results that are sometimes difficult to interpret. And I believe that doing analytical analysis of these slices, like for the 1 plus log slices, like for these shock avoiding slices, it allows us to gain insight into why it is that numerical simulations behave the way they behave. And that allows us to interpret the results with much more confidence than we would otherwise be able to do. So that's how I wanted to wrap up. I actually don't even have a time in my office, so I don't know how I did with time. I hope I didn't keep you too long. I know it's already very late in India, and I'm looking forward to my next cup of coffee. So let me just summarize precisely with my outline, with the outline that I started with. I hope I have convinced you that Yvonne Choquet-Brouillard's beautiful 1952 paper had a profound impact on numerical relativity, and actually thought it was neat to actually be able to actually trace how basically those ideas directly entered in these two formulations that are very commonly used these days, both the generalized harmonic formulation and the BSSN formulation. And I think this is not the only example where basically mathematical or analytical insights really help numerical simulations. And I gave you a couple of examples from these coordinate conditions where, again, I believe this analytical work helps us get insights and understand how they behave in these numerical simulations. And that's how I will end. I'll leave it at this. So thank you very much for listening, especially this late at night. And I'm happy to answer any questions that you may have.
Thank you so much, Thomas. That was an exceptionally clear overview of the field and how it relates to Yvonne Choquet-Brouillard's work. I believe Abhay had a question, and maybe we can start.
I can start, and I'll ask one, and then the other questions, please let them ask, and then I'll follow up again. This is a very general question, Thomas. First of all, thank you for this beautiful overview.
Thank you.
But one sort of, when we look at this, right, I mean, exactly a summary slide. So it brings out the following thing, and that I think is very, my question is really directed to younger researchers, or asking on behalf of younger researchers, if you like. So I mean, it was a seminal insight to use harmonic coordinates, but that was not quite right, because one had to change it, as Franz taught us, right, with the generalized harmonic coordinates. And then there's a BSSN formulation and everything else. Now, one gets overwhelming feeling that some general principles are laid out and they're very useful. But at the end of the day, really what is driving the progress for the last 30 years, or last at least 20 years since, is really these numerical experiments. I mean, in some sense, you don't wait for people to prove great theorems, which will say, well, what conditions you should use and such thing. But rather, you have these numerical experiments, and then in some sense you find some results, and then you look for an explanation for why is it working. I mean, it's a miracle, what's happening, etc. And of course, understanding that is important, because then it guides you a little bit in the future. But in a real sense, it seems to me that the ball has gone from hard analysis of PDEs and such thing to the numerical work. Am I right about this? Do you share this? Or are there instances in which, in fact, some hard analytical work, I mean analytical not in the sense that you are doing, but analytical in the sense of what Choquet-Brouillard was doing.
Yes, absolutely. Yes, and also, as I was basically giving this, I was preparing this talk, I also struggled with how can I make it clear that analysis is not the same as analytical work, right? So I completely want to acknowledge that, right? I agree, right? So basically, I gave you examples where it actually in coming up with these formulations, and be it Francis' work, be it anybody else's work, basically, I think we looked for inspiration in this analysis work, okay, and I think that was very helpful in guiding the development of these different formulations, okay. And I also agree with you that basically it is true that many of the, for example, the 1+ log slicing that was found heuristically. I mean, people just tried out things, okay, and then it worked, okay. But so there were also people who, when they first saw these results, they didn't believe it, because how could that possibly be? And I think actually the analytical work was then really important in convincing people, giving people reasons to believe that this is actually true. Okay. Now, I also, I mean, I said in my talk, really a lot of this is kind of to satisfy my personal curiosity. Okay, so for example, when we saw this different behavior for the 1+ log slicing and the shock avoiding slicing. Why is that? It's, if you only look at the equation itself, it is difficult to understand. Why would you see a qualitative difference there? So I thought it was neat to actually tease out what is at the core of this difference. Okay, but actually, so I think that, I mean, I gave you some examples where I believe that basically there's really complementary influences from numerical relativity and analytical work, but there are many other ones. Okay, so I think in the context of critical collapse, there's also very sometimes it really helps, the communication between both fields is really helpful, because there's some questions that are actually raised by numerics, okay, and then they're answered by analytical understanding. When Matt Shoptwick discovered these effects, it triggered a whole body of analytical work in trying to understand where that comes from. So basically, that was a beautiful example, I believe, of communication between different fields that are very complementary. Here's another question, okay, and it's something that I'm kind of curious about now, is I mentioned that in some ways it is very disturbing, it's on some level, that this lapse becomes zero. And when I talk about it, I get many questions about that. Why is it? I mean, essentially, in part of the space-time in your simulations, the proper time advances negatively. You're going back into the past, okay? Which is very appealing to the nostalgically inclined of us, but it's very disturbing for those of us who basically grew up, I'll say, with developing a 3+1 formulation from global foliations. Okay, it reminded me of a talk that Bobby Bike actually gave at a celebration for Neil Omudu in 2018, where he actually said, well, basically we start with these 3+1 formulations by assuming that we have a foliation, which implies that the lapse cannot become zero, leave alone become negative, okay? But he pointed out that actually you don't need to, that is not necessary in the end for the differential equations. I actually just exchanged emails with Bobby, and I'm hoping he will actually write up those results and firm those up, because it does, I think, there's motivation for understanding that better. Okay, so I'm not going to make a particularly profound statement, but I agree. I mean, there's basically, in some cases, this work basically was triggered in hindsight to understand this property, and of course we've made a lot of advances. But I do actually really believe that it's very useful to the complementary approaches. I think have been very helpful in understanding these results. Does that even begin to address or answer your question? Or
yeah, that's exactly. And also the difference between analysis versus analytical work, and what you described is really the interplay between analytical work and numerical work. And somehow analysis provided some general guidance, but is not really playing that much role now. And I think it's good for general audience to sort of realize that that's the state of that. Thank you very much.
Yeah, thank you.
So I have a quick question, Thomas. Slightly more technical. you described a few different slicing and gauge conditions that have nice coordinate singularity avoidance properties and shock avoidance properties. Could you perhaps also comment on the same for the original harmonic slicing and why the need for generalized harmonic gauge came up?
Right. So it basically okay. So for harmonic slicing, I gave you some examples here, right? Maybe I'll scroll back up. So harmonic slicing is one of those slicing conditions that is very easy to implement. It has been used by many people for various different simulations, and it works well, like in this example that I showed here, for weak waves. Okay, so you can use harmonic slicing and it works well, but it does not work well. It was found not to work well for black holes. And again, this is heuristic. Basically, people found by doing simulations with harmonic slicing, the code would crash. And why is it? Well, because it does not prevent you from actually from running into the space-time singularities and curvature singularities, and codes don't like that. Okay, they crash. So now there's also, in this case, analytical work. Okay, so to come back to it, and our distinction that demonstrated that. I don't think I had any reference to that, but there's also work that has been done to demonstrate that those coordinates will not work in general.
Thank you.
Okay, if there's no other questions, more, but if there's somebody else, then please go ahead.
Yeah, I'm not seeing any other hand up, so Abhay, why don't you go ahead?
Okay, so this is a kind of a question about coming a little bit from quantum theory point of view. I mean, there was a very nice review you might recall by David Brown, in which he many years ago now, in which he sort of pointed out that BSSN and various other things are very nice and they actually work, etc. But in some sense, one focuses just on the equations of motion and doesn't pay due respect to the Hamiltonian framework, which might be useful for quantum theory. And then he developed some methods to, he said that, well, there's one way of actually making it work for the Hamiltonian theory itself. And so, but then since then, that has just dropped out, and I don't see any strong use of that. Is it just because people are too busy, or is it that something goes wrong with that? Do you know? Do you happen to know?
So actually, you know what? No, I don't. You asked, do I know? But I don't really know. Of course, it is. I mean, in some ways, I think you find something that works, and then you go with that, right? And
yeah,
so
exactly.
People have used. I mean, there are different formulations around, and I mostly talked about the generalized harmonic formulation, and it would BSSN, but because just to make sure that those are not the only formulations. The Z4 formulation in particular, it is a really neat formulation originally developed by Bona and his collaborators. And that actually other folks, David Hilditch and Sebastiano Bernuzzi, and also Luciano Rezzola's group, they showed how that formalism can be cast into the framework essentially of the BSSN formulation. So you can have constrained damping terms that are not unlike what David Garfinkel had suggested. So that allows you to basically damp the constraints faster than without those terms. So just to make clear, right, time did not stop after this. There's been other developments. In terms of those Hamiltonian formulations, I'm not sure. Actually, I'm not sure whether people have used those very much. But I'm also, if not, I'm not aware of any reason for not doing that. Okay, so just other than in the context of numeric relativity, many people have their codes, and if once it works, why not do something with it rather than experimenting with other formulations?
Yeah, absolutely. I mean, yesterday I talked about also this connection variables for which the system is automatically symmetric hyperbolic from the beginning. So you don't have to do the tricks that one does for ADM. But that also is something that nobody took up because exactly for the same reason that you say, everybody has the codes that work, and so there's no reason to change. And the last question was really about hyperbolic slices. So this is not really so much about evolution of black holes or something, but really analyzing better the post-merger, regime, in which you might have a hyperbolic slice going from Scry to all the way to the common horizon that is formed. It could be the common dynamical horizon that is formed, that is evolving, etc., etc. So, what is the state? I mean, it seemed to me that would be something that would be very good to do to resolve some of the current disputes about the role of when the quasi-normal modes regime starts and so on and so forth. So, what is the status of that? This evolution, taking some data which is coming from numerical simulations, say, but on a hyperboloid slice, and then evolving it just using the hyperboloid slicing with that, because you already and staying outside the horizon, if you like. I mean, outside the dynamical horizon. So, what is the status of that kind of work?
You know what? I'm a little bit confused. What do you mean by a hyperbolic slice?
Hyperboloid slicing.
Okay, I misheard you. Hyperboloidal
I'm so
slice.
sorry.
Right.
Yeah,
Yes,
hyperboloid slices.
Yeah. Okay.
Which are going from the horizon all the way to Scry.
That's
and then,
right.
you get Scry itself. So that's a good thing. And then, I mean, some of the work in the numerical regime was started with Ansorg, and then was developed a little bit further by people in Copenhagen and so on. But I haven't seen very much work on that. I just wanted to know what the general impression from the numerical relativity community about hyperboloid slicing and their work.
So yes, there is ongoing work on that. And so, for example, I've mentioned David Hilditch a few times. He has done work on that. And several collaborators of his. Of course, as you said, it also goes way back. Okay, similar approaches were proposed by Helmut Friedrich in the 80s, I believe, maybe even earlier. Peter Hübner picked those up. So there's a lot of that. And I apologize profoundly to everybody else who I'm not mentioning right now because they're not coming to my mind. But so there's definitely a lot of work on that. Traditionally, there has been a fair bit of, or there's some issues. Essentially, basically, hyperboloid slices asymptotically become null as you approach Scry. Okay, and imagine you have outgoing waves. So basically, you now have to resolve an infinite wave train to infinity, and that can create numerical problems if you cannot resolve those many wave cycles, essentially. So, but nevertheless, there's a lot of ongoing work, and actually, it need a basic question: how can you generalize, for example, these 1+ log slices or these trumpet slices to hyperboloidal slices? I personally have not done any work in that, but I'm just observing it kind of the same way you are. Okay, but the answer to your question is there's definitely work on that, and of course I totally see the appeal. Right? It's a very neat approach to do that.
Thank you very much. Good to see you after many years.
Good to see you, Abby.
Okay. Does anyone have questions? I'm not seeing any hands up, so okay, I'm gonna go with no. So
very good.
I think we can conclude the session here. So on behalf of the organizers, let me thank Thomas once again for accepting our invitation, taking out the time to prepare and deliver this talk. Thank you, Thomas.
Thank you. Thank you all. Thank you for listening. Thanks for inviting me. Bye-bye.
Bye. And this ends this last session of the day. And tomorrow, again, we'll reconvene at around 2 p.m. IST, which is around 8:30 UTC and 3:30 Eastern Coast Time in the US. So see you all tomorrow. Bye.